How's quiz 3? No comments? A lot of points earnable on that. All right. Echem continued. Let's now consider an issue which as yet we didn't discuss. Take a look at the half reaction table, table 2. And pay attention to the half reactions for which an electrochemical potential is listed, but it's not an E0 value. It's not a standard electrochemical potential. You see which half reactions are under consideration? You'll see one which involves hydrogen as a reducer. And another which involves oxygen as an oxidation product, operating at pH 7. Since these two half-cell systems depend on the hydronium ion concentration, and under standard state conditions, concentrations are what value? 1 molar. So the E values listed cannot be E0 values, since the two half cells to which I am referring are operating at pH 7, where the hydronium ion concentration is hardly standard state. So when you tackle question 24, which involves the oxidation of copper in the presence of hydrogen sulfide ion in the basic system by oxygen in the presence of water to make hydroxide ion as product at pH 7.00, what are you going to use for E0? Because to operate, to apply the Nernst equation to this system, you've got to have E0 cell. And you can't get E0 cell unless you got E0 for each half reaction. Any suggestions? What are the possibilities? What E0 values could be used? Give me the numbers. Read them from the table.
14.
I want the E0 values that could be used. What E0 values can we write here? There are two of them.
0.40.
What is that?
0.40.
You can use 0.40. Same system except that
pH 15.
we're at pH 14. Does that correspond to standard state hydroxide ion? You betcha.
And 1.23.
We could use 1.23. That's standard state hydronium ion. Now we'd have to change the equations we'd write here, but it wouldn't change the operating potentials which we're going to calculate. So I'll put down 0.40, change this to 14.00, and keep in mind that what I'm asked to pay attention to is this system operating at pH 7, which will come out in the Nernst equation. Here's the Nernst equation. Now, I can do this if the hydroxide ion molarities compare how? If they're equal. But if I can construct this system so that the hydroxide ion molarities are different in the half cells, which means I would have to physically separate for this system the oxidizing half from the reducing half. So, as I did previously, I'll apologize for a poor choice, because this is a poor choice to illustrate the point. Because in this system, the reducer is copper, which is solid state, not in solution. And the oxidizer is oxygen, which is gas phase, also not in solution. So I can run this system with the solution components all swimming around in the same pot. And if I have the solution components swimming around in the same pot, I can't create two different hydroxide ion molarities. So if I want to run this system in accord with the way the question is stated in the notes, or the consideration is placed with respect to this question, I'd have to set up this system so that, as we did in our demonstration, in one beaker I've got the anodic half cell components, and in the other beaker I've got the cathodic half cell components, and then I can have different hydroxide ion molarities. So, I'll go back to this and keep in mind that I can have different hydroxide ion molarities if I construct the system as I have just described. You'd have to put the anodic components in one separate container, a beaker, whatever you want, the cathodic components in the other beaker. So you've got physical separation between all the anode compartment components and all the cathode compartment components. Under those conditions, when you put in the hydroxide ion molarity of 1.0 times 10 to the minus 7 at pH 7, you'll get an E cell of 1.08 volts. Which of these hydroxide ion molarities is the hydroxide ion molarity for this system? Is it this or this? Top one. You can do the arithmetic. Now, one more question which parallels an issue we've already discussed. But it's important because it requires you to understand how to put to use the information in this table. And you can rest assured on exam 3 there will be questions which are just like this. If I have this system in operation and I make available to you 1 molar hydrochloric acid solution. Remember the copper ion, zinc ion, copper zinc system? And I said with 6 molar ammonia, what could you do with the ammonia to make E cell go up, E0 cell go up? Same question here. With 1 molar HCl made available, can you operate on this system? Can you treat this system with the 1 molar HCl so as to make E cell and E0 cell go up relative to what they are presently observed to be? So the possibilities are: add HCl to the cathode compartment only, to the anode compartment only, which again means I got to put the system together so that the anodic half cell is separate from, physically separated from the cathodic half cell. Now I can build a system like that, so that's not a problem. So would I add the HCl to the cathodic compartment only, the anodic compartment only, both compartments, or neither compartment? 4 choices. Only one of which is right. And if I ask a question like this, and you identify the correct choice, I might, if I'm in a good mood, give you 1 point. And I don't give a damn about votes. I care about chemistry. You got to tell me why it's the right choice. So what's the right choice?
Cathode.
Cathode compartment. Why is that the right choice?
Because if you add it to the anode, it will murder all the hydroxide and it'll give you...
What else will it murder?
The HS minus.
Mm-hmm. Adding HCl solution is the same as adding hydronium ion and chloride ion. Hydronium ion, as you well know, kills hydroxide ion and kills HS minus. If you examine the half reaction information in table 2, you will see that copper, remember we recognize copper is not a very good reducer, is it? When it converts by oxidation to hydrated copper ion. For that, the operating potential is negative. But here, copper is again the reducer, but now it's being given the opportunity by oxidation to convert to copper sulfide in basic media. And now the E0 value is plus 7.6 volts, as opposed to minus 0.34 volts, which is what you observe when copper is oxidized in water to hydrated copper ion. Well, you made copper a hell of a lot better reducer by giving it the chance to form the sulfide under basic conditions. Well, what do you do to the tendency of forming a sulfide in acidic conditions relative to basic conditions? Is it more likely to form the sulfide in acidic conditions? Acid-base chemistry students? Hell no! Sulfide's a potent base. The more acidic the system, the more effectively you murder sulfide. The half reactions tell you this. There should be a half reaction on there where copper is oxidized by H2S in the presence of hydronium ion. You see that one? What happened to E0? You still get copper sulfide, but the E0 value is a whole lot smaller than 0.76 volts. However, regarding oxygen as an oxidizer, the reason in the main why I put these half reactions in there, which are not standard half reactions, the ones which function at pH 7 with hydrogen as a reducer and oxygen as an oxidizer, is so that you will see for sure how oxidation strength and reduction strength depends on system pH. Now you already know about that because we made that consideration when we did our redox demo. And showed, for example, that zinc at pH 7 does not react with water to make hydrogen. But you put zinc in pH 0 water and out comes the hydrogen. So when you look at these half reactions, what do you do to the reducing power of hydrogen as you make the system more basic? The standard hydrogen electrode is where you're starting. There's hydrogen being a reducer at pH 0. What happens to the strength of hydrogen as a reducer when you make the system pH 14? Goes up a lot. So at pH 7, you know hydrogen is a stronger reducer than it is at pH 0, but not as strong a reducer as it is at pH 14. Now what about oxygen as an oxidizer? We just answered the question, didn't we? We recognize that by taking this system and treating only the cathodic half cell to give oxygen the opportunity to be an oxidizer in the presence of hydronium ion, not hydroxide ion. Does E0 go up? To what does E0 rise? If the hydronium ion becomes standard state hydronium ion, pH 0. 1.23. Because oxygen as an oxidizer means we're turning that half reaction around. So, the ability of something to be an oxidizer is best in acidic media. The ability of something to be a reducer is best in basic media. Have you ever recognized how this, or pardon me, I shouldn't say have you ever, because you probably never thought about this before. But you should now be able to see some relationship of this consideration to food spoilage. Have you ever noticed which foods in the refrigerator will keep longer as a function of pH? Which foods as a function of pH spoil more rapidly? I mean, maybe you never paid attention to this, and I wouldn't be at all surprised. This is something I thought about after teaching this stuff for a while. Spaghetti sauces, for example, are made up in tomato. Tomato stuff is rather what? Acidic. That keeps a long time. Because if anaerobes or bacteria, whatever, get into the tomato sauce, the acidic media oxidizes them buggers. It kills them. But the basic foods, they're good reducers, which means they react readily with oxygen, and in so doing, spoil. Now, I'm not telling you to go home and for every food that you have in the refrigerator that you want to keep for a good while, treat it with some hydrochloric acid solution. That might have a significant impact on its flavor. But materials like orange juice, tomato juice, acidic, they keep a hell of a lot longer than milk. You think there's a big difference in the pH of these systems? All right. Question 25. I asked you about question 25 on yesterday's quiz, because I saw no reason not to do so. Look at table 2. If you want to use table 2 information and the Nernst equation to calculate KSP for this stuff, which half reactions will you use and how will they be coupled? Statement. If I haven't said this before, but you should know this because it's in the material, in the notes, that discusses uses and application of the Nernst equation, like how to make a pH meter and stuff like that. Did you read about that? It's all there. Only a couple pages of chat, and it's your job to read this stuff. I think it's fair to say the most common use of E0 information is to calculate K values, equilibrium constants. So here's a particular equilibrium constant, the likes of which we are familiar, because we talked about KSP equilibria in chapter 19. If I want to use table 2 information plus the Nernst equation to get KSP for that stuff, which half reactions do I use and how do I couple them? Tell me the numbers for the half reactions. I don't want the E0 values, I want the numbers for the half reactions. 22, 15, any others? Because other people may have different opinions. 9? Any others? I'm listening. Clearly only 2 of these numbers can be right.
That one I think you get from the other sheet.
What is that? Now I'm talking about table 2 in the notes, not the information sheet.
Then definitely not number 9.
Good. Because as you should by now, I think, recognize, the table 2 that's in the notes is a more comprehensive list, is a longer list of half reactions. I don't want to give you an information sheet that's more than one piece of paper. So the half reaction list on the information sheet is a shorter list. But if somebody said 9, then it strikes me that you were thinking correctly about this question as it was asked yesterday. 15 and 22. Because what you have to keep in mind in answering this question is, what is the equation for the reaction for which the K value, by definition, is KSP for that stuff? If you know that, you're in business. So we'll write. Because as you know, KSP is an equilibrium constant, which is a measure of the tendency of a salt of limited solubility to fall apart into its component ions in water solution. So if we turn the KSP equilibrium reaction around, we're asking the question, which ions have to react to make this precipitate? Well, what ions react to make this precipitate? What are the ions produced then when this precipitate dissolves in water? Tell me the ions. Hydrated iron. There's a nail with water molecules stuck to it. That's hydrated iron. That's not it. Did you not learn that these are each not formulas for sodium? Have I not yet told you about the sodium ion tongue test? When I teach 2045, in order to get students to understand how careful we have to be in communication in science. And we get at this when we learn to write formulas for materials. And I have a bunch of students in 2045, because they're just learning, they don't know any better, who will insist that both of those are formulas for sodium. And I say, you who said that, you come forward. Okay? So this poor soul steps forward, and I say, okay, stick out your tongue. And I take some sodium chloride right out of the box of Morton's that I have in the back, teaspoonful, put it on the tongue. I say, reel in your tongue and describe to the class your sensations. I say, well, there's a salty flavor. Yeah. And if they're careful, they say, I experience a little bit of cooling. Because sodium chloride dissolves in water, endo. It's a heat-consuming process. Okay? It's not significantly endo, but it is endo. So if you're careful, you'll experience the sensation of cooling as the sodium chloride is dissolving on your tongue. But that's it. I say, now notice, you just took in a sample which is very rich in that formula, and you told me that's sodium. So I say, put back out your tongue, and I squirt it off with deionized water, and then I take a nice big piece of sodium, maybe a 2-3 gram piece. If I really don't like this person, it'll be a bigger piece. Now put it on the tongue and say, reel in your tongue. Pow! And then I say, describe your sensation, but the student has no more cheeks. No more teeth. No more student. Can't describe anything. But I assure you that person will never again tell me those two damn formulas mean the same thing. You get the idea? All right, let's go back to this formula. Formula writing activity. I want the iron-containing ion over here. What is it? Hydrated iron. Ion. On your information, on the table, half reaction table, there are 2 hydrated iron ions on there. Which one are we talking about? Ah, that's better. Now what do you think this thing is going to react with to make this thing? That's all right. Believe me. I'm not nearly as mean and nasty as I may sound. This is the hardest part of chemistry. This is real chemistry. What are the formulas for materials? How do you write equations for reactions? How do you inventory a system? You know how much time we spend with that this term? You know how much time textbooks spend with that? Nothing. And they wonder why in the hell the students are not learning chemistry. Well, you don't teach chemistry, damn it. How are you going to learn something that's not being taught? I tell this to my colleagues, but on we go. Do we have a missing reactant or product? I'm giving you a clue here. How many? And so, when we apply Nernst, we've seen the reaction equation. And we know KSP values are all numbers which are notoriously smaller or larger than 1. Smaller or larger than 1? KSP values? Smaller. Hey, these things are salts of limited solubility. They do not readily decompose into their component ions. They don't readily dissolve and dissociate in water solution. So I know, before I do this arithmetic, that the E0 value that I want or must use to allow me to calculate KSP for this stuff is going to be a negative or positive number? Negative number. So that tells me, of course, when I got this reaction equation, that also tells me how I couple 22 and 15. Which one of these gets reversed in this coupling process? 15 gets reversed. So that when I put these values together, I got a negative E0 value. So I will write E cell equals E0, which is a negative number, minus 0.059 V over 2. That's moles of electricity transferred in this system. Times the log of what? Log of what? Which K? KSP, yeah. So I need one more consideration. What is this?
0.
We're at equilibrium, are we not? Whenever I calculate an equilibrium constant with the Nernst equation, E cell is 0. Equilibrium. All right? So we take a look at concentration cells. Interesting cells, to say the least. Here's a picture of a beaker containing a strip of copper standing in a solution containing hydrated copper ion. Same over here. Now, as things presently stand, I've got the components of this beaker connected to the components of this beaker by my salt bridge and by my piece of wire. And in this piece of wire, I've fused a socket, and this is my Van Gogh representation of a light bulb. So if this system delivers usable electrical energy, ha-ha, my light bulb will glow. Let there be light. All right? Now then, before we talk about lighting up the light bulb, let's take out the salt bridge Because when I take out the salt bridge, there's no way the light bulb can glow. I cannot have a circuit complete from this beaker to that beaker. So the salt bridge is out. The copper strip is touching the hydrated copper ion. Are electrons flowing? Does a reducer reduce its own conjugate oxidizer? Does a conjugate oxidizer oxidize its own reducer? The answer is you betcha. It sure does. It's rather like an equilibrium system containing 1 molar acetic acid. If you have a beaker of 1 molar acetic acid in the laboratory, where the equilibrium is, HAC molecules, aqueous phase, plus water, double arrows, hydronium ion, and acetate ion. In that system, as you look at it, are hydronium ions and acetate ions reacting to make acetic acid molecules and water molecules? In that system, as you look at it, are acetic acid molecules reacting with water molecules to make hydronium ions and acetate ions? You're damn right. And that's happening here too. Except, of course, as we know, this leads to no net chemical change in concentration or composition of the system. Now back to our concentration cell. Here's an equation for a net cell reaction for a concentration cell. A copper-copper ion concentration cell specifically. As this copper reduces this hydrated copper ion, I produce this hydrated copper ion as the oxidation product, and this copper is the reduction product. Question. On what does E cell depend for a concentration cell? Well, before we get to that, let's go back to this part of the puzzle. What's E0 for a concentration cell?
0.
Got to be 0. The half cell which corresponds to oxidation is exactly the same as the half cell which corresponds to reduction, except one of them is reversed. So for this cell, for copper becoming hydrated copper ion, the potential is, half cell potential is, minus 0.34 volts, and when I turn that around, it's plus 0.34 volts. So for any concentration cell, E0 is 0. So I ask the question, on what does E cell depend for a concentration cell? Does it depend on delta H? Does it depend on delta H 0? What does the measurement of delta H for chemical reaction system tell us? Tells us about bond improvement or disimprovement, as the case might be. Exo bond improvement, endo bond disimprovement. Can this reaction be exo or endo? Can this reaction be exo or endo? However many copper atoms I oxidize has got to equal the number of copper atoms I produce. However many of hydrated copper ions I reduce has got to equal the number of hydrated copper ions, however many the number of hydrated copper ions I reduce has got to equal the number of hydrated copper ions I produce. E cell depend on this? 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 Be careful. What's this mean? Standard state. So delta S0 means what is delta S for this reaction under standard state conditions? And if it's under standard state conditions, what's the molarity of this? There it is. It's rather like the entropy of mixing. I could ask if you heard about the entropy of mixing in 2045, where you should have heard about it, but I expect that you didn't. Question. if you go home and you dissolve a package of Kool-Aid, your favorite flavor, in a pint of water, okay? In this big 1-gallon decanter. You've got a package of Kool-Aid dissolved in 1 pint of water. Let's imagine it's cherry Kool-Aid. So this is a nice, pretty cherry red color solution. I now take another pint of water and pour it on top of the Kool-Aid solution I've already prepared. If I allow this system to stand for a good long time, remember I poured the straight water on top and I started with the Kool-Aid solution at the bottom. If I come back in a week, will the water on top still be colorless? Will the Kool-Aid solution at the bottom still contain all the cherry red color and be as intense in color as it was when I first made this system? Why not? Is liquid a dynamic state of matter? So even though you're looking at this, it doesn't appear, as you see, it doesn't appear to be any movement in there. You know doggone well that on standing, there will be a net migration of, let's call them Kool-Aid molecules, from the bottom part of this system to the top part of this system. Now they'll keep going back and forth, but there will always be a greater rate of migration of Kool-Aid molecules from the bottom of the system to the top of the system until equilibrium. When will equilibrium be achieved in this system? When the Kool-Aid concentration is what?
The same.
The same how? Where? Be more specific. In every part of this system, which means now I'll have a true Kool-Aid solution. What's driving this mixing? It's called entropy. Because, from an entropic standpoint, the resulting solution exhibits the most stable thermodynamic state in which this solution can exist. That's why it goes there. Same thing here. So, to make a concentration cell, what I have to do is to use, let's say for this case, two molar copper ion and 0.02 molar copper ion. Let's call this beaker A, which means by default this is beaker B. In beaker A, do you wish to place the 2 molar copper ion or the 2/100 molar copper ion? Let's have a vote. Beaker A, how many wish to put the 2 molar copper ion? The 2/100 molar copper ion. Most people didn't vote. So most people will have to drink this solution after we make it. That's the penalty you pay. We're going to turn you into a concentration cell for our benefit. And we'll plug the light bulb into your ear to see if the damn thing lights up. How's that? All right? This is here, so by default, this is here. If this is the way I construct this system, Which of these beakers is the anode compartment? Which of these beakers is the cathode compartment? Say again. A is anode. Any votes to support that? Any votes to support that B is the anode compartment? Bunch of non-voters again. You get to drink the 2 molar copper ion. Or did I already give that to the other people? I'll make something else up. If I have here 2/100 molar copper ion, and here I have 2 molar copper ion, then it is true that the electrons will flow this way. And here, ions will travel this way. Of course, there's negative ions in here as well. And this will be the anode compartment. And this will be the cathode compartment. But I could just as well have put the 2 molar copper ion here and the 2/100 molar copper ion here, except now I'd have polarity reversal. And this would be the anode compartment, and this would be the cathode compartment. But I expect that most of you who voted for putting the less concentrated copper ion in this beaker are just taking off from the fact that we said when you draw pictures of this, it's standard practice to show the anode compartment on the left and the cathode compartment on the right, so that's fine. No problem there. All right? How long is this system going to run? And I don't want any time answer. Until equilibrium. Well, under what will be the condition which defines equilibrium for this system? When I have an equal molarity of copper ion in each beaker. Because as 2/100 molar copper ion, as copper in the 2/100 molar copper ion is being oxidized, I'm making more copper ions. And as copper ions are reduced in the 2 molar copper ion, I will be reducing the molarity of copper ion. And this thing is going to continue to operate until I get equal molarities of copper ion. All right, the remaining 2 issues for chapter 22 are that of galvanic protection, and derivation of E0 values for new half cells. We'll get at that next time, but I'm going to leave you with this directive. To get at chapter 23, because we will be at chapter 23 next time in great detail. And what I'm going to tell you now is that I want you to read chapter 23 carefully through page 2318. Oh my, that's a lot. Just about all of this will be review. So you should be able to get through it in a rather expeditious fashion next time.